Howdy, everybody. We're here for day 24 of Advent to Code 2015. We're almost done. Still playing around with the look and feel of everything. Love to know your opinions, how you like it, or what you like. Anyway, we're getting close. We just got 2 days left. Sometimes the last 2 days are the hardest. Although in some years, the last day is relatively easy because you often only have one part to it. So anyway, we'll see whether that holds true or not with this problem. But, you know, as always, love your comments, love your, any insights you have on ways to improve or to get better. Like, for example, last time, I just don't think Nom was the choice for it, but you know, your opinions, love to hear what you think about it and everything like that. So with that, let's get started with day 24. So this one is entitled It Hangs in the Balance. It's Christmas Eve and Santa is loading up the sleigh for this year's deliveries. However, there's one small problem. He can't get the sleigh to balance. If it isn't balanced, he can't defy physics and nobody gets presents this year. No pressure. Santa has provided you a list of weights of every package he needs to fit on the sleigh. Okay. The packages need to be split into 3 groups of exactly the same weight. And every package has to fit. The first group goes in the passenger compartment of the sleigh, and the second and third go into the containers on either side. Only when all 3 groups weigh exactly the same amount will the sleigh be able to fly. Defying physics has rules, you know. Okay. So the idea is we have 3 groups. We want to make 3 groups of the exactly same weight. Of course, that's not the only problem. The first group, the one going in the passenger's compartment, needs as few packages as possible so that Santa has some leg room left over. It doesn't matter how many packages are in either of the other 2 groups, so long as all of the groups weigh the same. Furthermore, Santa tells you if there are multiple ways to arrange the packages such that the fewest possible are in the first group, you need to choose the way where the first group has the smallest quantum entanglement to reduce the chance of any complications. The quantum entanglement of a group of packages is the product of their weights. That is, the value you get when you multiply their weights together. Only consider entanglement if the first group has the fewest possible number of packages in it, and all groups weigh the same amount. Okay, so it's saying split into 3 groups. The first group needs to have the smallest number of packages, or as few packages as possible. So like of all the ones, of all the options, find the one where group 1 has the smallest number of packages in total, but also the smallest quantum entanglement, which is just the product of the weights. So you just multiply them all together. Okay. For example, suppose you have 10 packages with weights 1 through 5 and 7 through 11. For this situation, some of the unique first groups, their quantum entanglements, and a way to divide their remaining packages are as follows. So it just gives you an example, right? Like the smallest one is 11.9. All the other ones are larger, so you'd pick this one. But if there were duplicates, then you'd pick the lowest quantum entanglement. Of all these, 10.9.1 has the smallest quantum entanglement. The configuration with only 2 packages in the passenger compartment gives the most legroom and wins. So yeah, so like even though this has the lowest quantum entanglement, this is the smallest box. So there's clearly a precedent of split into 3, smallest box, least quantum entanglement. In this situation, the quantum entanglement for the ideal configuration is therefore 99. Had there been two configurations with only two packages in the first group, the one with a smaller quantum entanglement would be chosen. What is the quantum entanglement of the first group of packages in the ideal configuration? Okay. So how to solve this? Well, let's look at our input size. A lot. We may have to do some math on this. So I'm interested in maybe like doing some pre-processing to like find stuff out. So let mute weights. I'm gonna want to sort it, so that's why I'm doing mute. Input dot lines dot map. Will that work, or do I have to specify the parts? Parse. No. Okay, it figures it out. So I'm gonna print line the weights, like all of them. Oh, I was gonna sort them. Were they sorted? They do look like they're sorted already. Yeah. So maybe I don't need to sort them. I also want to know what a third of them is, and their sum. So let's so we can calculate the weights dot iter dot sum, and then so let the, I guess like we can call this the total, and this is the whatever the group total. Okay, so I just want to do these because I think they'll give us some insights. Oh, total divided by 3. Okay, the reason why, I don't know, can you see the mouse over here? This is like interesting is because it does give us some idea of how many weights are there. Like some bounds. So there's 29 weights going to 1536. So if we do like 1536 divided by 29, so on average each weight is about 52. And I need to get to 512. So on average, if I was just picking randomly, I would need about 10 weights to get to it, or I guess 10 packages. We can call this packages. Okay. So another thing to think of is like, well, here's what's going through my mind is, I guess I should explain myself. We clearly can't do like pure permutations because there's 29 of them. So like, what is 29 factorial? Well, I guess we could do it right here. Sorry, one. No. It's this, right? 29 factorial is 8e to the 30. So like we're in the decillions or whatever. An absurdly large number, which is not very helpful. But let's say we know the smallest size is 5. So there's 29 objects and we want to pick 5 from them. We only have to do 118,000 combinations of those 29. What if it was like 4, 3, 6, 400,000, 7? This is when you get into the millions now. So 7 is a million. So if you were to say like, oh, I know the size is 1. Now I only had to, find the 29. But if it's like 7, say the size, we know the smallest size of the thirds has 7 boxes or 7 packages, then we know that we'd only have to check like these 1 million and find the smallest quantum entanglement. Does that make sense? Yeah, like, so what's going through my mind is we actually don't care about these groups right here, groups 2 and 3. We really only care about group 1. So the thinking is, can we come up with some kind of number of combinations and see which can we come up with what we think some range of like the smallest set needs to be for that first group from all of the numbers. And if we can do that, we can kind of iterate it through them from smallest to largest, right? So but we had to find one that's exactly 521. Is that what it was? Is that what I figured out? Oh yeah, I guess it's over here. 512. So we want to min max it too, right? So what is the minimum number? Oops, I don't want to do that. Like if we're looking at this, what is the minimum number? 1, 2, 3, 4. You could definitely fill 512 with 4 boxes, or yeah, with 4 packages. I mean, not exactly. These are like rough estimates. So we probably have to start at 4. So we say, give me all the combinations of 4. But then how do I maximize it? That can go quite high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like these numbers, we're not getting into, like if you think about it, like these are 20, 60. like you're not getting to like right here. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, like somewhere in the 19 range before you get to 512. So we may have to go as high as 19, which is absurdly high. That makes me wonder if there's like another way to do it. Oh, no, that's not the case. Like, suppose the smallest... We want the smallest number of boxes. It's never going to be more than 29 divided by 3, right? So 8, is that right? $10. I mean, 10 factorial is still a lot, but that does give us a range. So we know we can start at 4 and then go to 10 to try and figure it out. So again, the theory is we're really only interested in the number of weights in that first box. And so we can use my combination thing to generate all the combinations of 29, pick 4 and see if we get one that's 512, and then we sort by the lowest, and then we do 5, 6, 7 all the way up to 10. We just do that all over until we find them. I think that will solve it. If we go up to 10, what is 10 factorial? It's like 3 million. And then like 9 is like 2 million, right? No, not even close. 3. So in total, you're doing like 4 million checks. Maybe that's not hard. Maybe that's not a lot then. So I think it might be okay. So here's what we do is we say like for I in 4.10. Oh, it would be 9, right? Because if it was 10, the others would have to be some combination of 10 and 9. So it is 9. So the does that make sense? Like the most I can ever put in the first box is 9. If I ever put more than 9 in there, then I would never have enough. But this actually has to do with it's more akin to this number right here. These numbers are a little fudgy because they may be different for your input. So this may not be like a generalized solution that we're working on. But let's see, we're definitely going to return a U size. So, but how do we do this? We say like for combination in combinations. Packages.lane and 4. Oh, I like that. Is that the right? Create a new combination iterator for an n size array where k elements are taken from each iteration. Yeah, so that is right. Okay, so we're going to have the combinations, and then we want to do the sum. Oh no. Yeah, we want to check that those combinations are equal to 512, right? So we say let s equals, we can rename all these variables and stuff. C dot iter dot map. Like that. Why isn't it like some? Missing that maybe. Okay, so if s does not equal group continue. I think we can do some of this in a functional way. We'll see. So min equals min dot min of this same thing, but the product. Like this is the quantum entanglement. So pick the minimum of the max and this. And then we can say if min does not equal u size max. Like if we found 1, then we can return min. Otherwise we return 0. I'm curious where it stops, so we'll do print line. Like that, maybe? Is it running it? Ooh, it is taking a little bit of time. Ooh, 14 seconds is not like a great solution. So I wonder if there's some, I could try. Sort by A, B, B comp A. So this is the equivalent of like doing a reverse sort. Oh, do I need, is it like this? Does that make it faster? Like presumably it finds it faster. Maybe. Oh, I know this. Well, I know the size is 6. So that helps me get it somewhat faster. Oh, do you know why it's always the same time? Because I have to go through all the combinations. Sorting doesn't actually help because I have to go through all the combinations. This is definitely not optimal. So we may we may keep working on this one. Okay, that is the right answer, though. I mean, I presume it would be the right answer, mostly because I'm literally trying all the combinations until I find the right one. And because I know it's 6, again, it's only 6 for my solution. That helps. But okay, let's try part 2, and then we can see if we can refine it. That's weird. The sleigh still isn't balancing. Ho ho ho. Santa muses to himself. I forgot the trunk. What? Okay, balance the sleigh again, but this time separate the packages into 4 groups instead of 3. The other constraints still apply. Given the example packages above, this would be some of the new unique first groups, their quantum entanglements, and one way to divide the remaining packages. Of these, there are 3 arrangements that put the minimum 2 in the first group. So those 2 in this one. And the lowest QE is 44, right? 11.4, yeah, has the lowest QE, so it's the one that's selected. Now, what is the quantum entanglement of the first group of packages in the ideal configuration? So this is the same problem, just we're now dividing by 4 instead of 3. U size. That does change these numbers. It technically shrinks. I still think 4 is the minimum. So you divide by 4 the group value. Divide by 4. I think you still start at 4, but this potentially won't go to 9 anymore. I think this is going to solve it, so I'm not inclined to worry about it too much, but I'll leave those in there just so we can see how we did part 1. I have to wait 15 seconds for part 2. This is where, like, if you're like solving competitively, 14 seconds is probably okay, assuming you got the right answer. But doing it twice, I guess 14 is nice. It's like not too bad, right? So, ooh, could it be 3? No, it was size 4. It took 9 seconds to go through all of 4. That's crazy. That is the right answer. Day 24. Okay. Yeah, so is this the most optimal solution? Probably not. I mean, I definitely think we can. Let's see if we can't. I mean, it's kind of cheating, but because we know it's 6, we can do something like this. Combination. New packages.line 6. And then we want to filter on oh, actually we can map them. First. So it's C iter map. I think this is still the same. So what we do is we take the combination values, we map them to the package values, and then we can filter where the packages dot sum USI does not. No, we only want to keep them where it equals group. And then we want to map them to their quantum entanglement, which is like that, maybe. No method name inner found for struct map in the current scope. Oh. Yeah, I can't do that. I need to collect this one, huh? Oh, I just need to iter on this one as well. Oh, it's because it doesn't know what this is. Unwrap it. Does that still get me the solution any faster than 21 seconds? I mean, it is faster. Again, because I've skipped 4 and 5, right? I don't have to try it at all for 4. How many was pick 4? 23,000. Pick 5. 100,000. It's not a lot. But they still take several seconds, right? I can also do. I mean, this is kind of cheating because I have 6 right here. Like my original thing was 04 to 9. And I think I'm fairly certain that like doing that kind of math is like, yeah, I can. This is like what you do some with these problems. I don't know if you've ever done like problem solving Sudoku or other things like that. Is you kind of like use the constraints to like whittle down like to get to a range or to even a specific number that could only be used. And so in this case, we're saying like we know at a minimum it's 4. Right, we would need 4 to make 512. but we could never make more than 9 for the other constraint, which is it had to be smaller. So given these constraints, I think you can get down to this. Okay. I mean, I can still go. Yeah, so what I can do is I can say, like, I can put this in a for loop for I in 4 dot dot equal 9. I can say let solution equals this, and then if it's we match on solution, and if it's sum v, we return v, otherwise we continue. Like, this is like the more generalized solution to how I did the last time. So I guess I can do the same thing here, down here, because I do think this looks cleaner. Yeah, I think technically this one could be 3. Could it be 3? At least for mine, 1536 divided by 4 is 384. No, you still need 4, right? You definitely need 4. You need 1, 2, 3, 4. Oh, I was counting wrong, huh? So for 384, I can't do it with these 3, so I definitely need another one. I need a 4th. But for 512, 1, 2, 3, 4 is not enough. So I definitely, for part 1, I actually can start at 5. This one I do need to start at 4. But again, neither of them can go past 9 because of the box condition, right? I need to have the smallest number of boxes in there, and so any solution where I had more than 9 wouldn't be a valid solution because it meant one of the other places had more. Ooh, this one's even less. It actually, I mean, we know it solves in, what was it, size 4? So that doesn't really matter. But this one technically, because I should have thought of this one more. It is 4 to 9, but it's like 4 and 29 divided by 4 is 7. So if I ever have more than 8, yeah, so I can go to 9. Or sorry. If I ever have 8 or more, it gets me more than the number. And I guess the way you figure that out is you do what we were doing there. So you can make this more generic, is we can say this number is actually equal to packages.len divided by 3. Right? And then this one would be packages.len divided by 4. And I think that still solves it, but now you don't. You've reduced the scope as far as you can. let's see. Okay, so that does give you the right number. I'm inclined to look for solutions. See if there's a... but the solution didn't require looking at anything further than the first group of packages. The remaining groups all divided evenly. Yeah, I think, well, this is not really helpful because all of the groups have to divide evenly. So maybe that's misunderstood. Looks like they did the same thing as me. Some weights. I think they're doing the same thing as me. Yeah. He starts at 0, or I guess, yeah, 0, but yeah. Okay. In the submissions posted so far, the assumption is made that if you find any group with the right weight, the other groups can be made. This isn't true in the general case. Consider list 159. Yeah, I don't think this is the... We actually don't care. I mean, you are... That is an interesting problem. Like, technically, the weights could be distributed in such a way that, like, let's say you get 512, and so the rest of them are, 1024 or whatever. There may be no way to make 2 groups of 512 from those. That's actually interesting. The number of ways to make 512 may be small enough. Because think about it, you can't pull from here. We know we can't pull more than 9. 5, 6, 7, 8, 9. You can definitely make 512 from these like upper bounds. Like what was going through my mind is like, can you say you have to have one of these 100 numbers to get there? I don't know if that's the case. But a lot of these are really just... My guess is people are doing combinations. Branch and bound could be faster. Ooh, although it pruned correct solutions. That's a good point. It could prune them, so I'll have to look into branch and bound more. That might be a faster way to solve it. Yeah, this would not work, right? Trying to do them all. It was a list of primes. This was not helpful. What the? I mean, I can't say for sure, but it does appear to be a list of primes. Okay, I had not thought of that. If all three groups have the same weight, then the weight of one group is the sum of all the packages by it. Because if I found a group that summed to that 512, the rest of the packages had to be divisible into that. It would be impossible for less than 6 numbers combined to total that. Yeah, that was what I was thinking too. Since it wants the smallest group, why 6? I think you can do it in 5, right? $500, yeah. That may, I mean, maybe for her input or their input, it may have been 6. Mine was 5, I think, right? I did mine in 5. Yeah. It does suggest reversing the input makes it faster. I don't know why reversing it would make it faster, because you have to check all of them in the thing. Yeah, so like for each get permutations. Look for combinations that add up to the correct answer. Yeah, a lot of people are just using combinations. So maybe there is no... I was hoping maybe I would find someone that had some fun math stuff that said, here's how you solve it. It doesn't have a combination. Yeah, I built my own in Rust. Yeah, like this assumption though, I think is a valid assumption, right? So when I was talking about this earlier, like we only care about group 1. What we assume that the other group can be done as well. Is that a valid assumption? I suppose in this general case, it's not. And so you may have to, for it to actually be solved for the general case, you still do the combinations over the groups, but you do an additional filter where you say, can I partition the rest of them into a group of 29? Which you could probably do in like n log n time. It makes it definitely increases the complexity and makes it harder. But that is an interesting assumption. I actually don't know in the general case. It turns out that it worked. I should have thought that through too, because that might... Well, I mean, I got the right answer. So, haha, what do you do? But there might be an argument for having thought that. Like, if my solution was wrong, this assumption might have been something that was worth looking at. Okay, this person has a combination package in nim. Same thing. think all of these are doing combinations. YXW. What the? Yeah, a lot of people never check the balance. What is he doing here? Min product inputs. Sum over 3. 0 and 0. So you have the inputs, the weights, cumulative product and cumulative weight. Okay. Does this solve it faster? Huh. It might. We can try and do this one. So what they're doing is they're saying what is like the minimum product, right? So what is the smallest? Input weight requirement. Index I plus 1. What are they doing here? Does this actually work? I'm going to move this. Well, let's see here. Let's just do it with P1 recur or P1 right now. So I still want to do that. Oops, I want to call this one P1 recursive. So this is the QE, which is a U size, and the weight, which is a U size. And I'm going to return a U size. 0 for right now. So we're going to return P1 helper packages start at 0, 1, 0. And then we say if the weight is equal to the requirement. Oh, I guess I need to include the weight requirements as well. So if required equals weight return QE. We just need like a thing right there, right? So otherwise we're going to call this on this is if we do nothing. Like we don't include it. Right. I can have this return sum or an option. We can fix that in a minute. What? I swear sometimes Windows eats my inputs. Oh, I lost my left. Oh no, it's right there. What the heck? Okay, what? What doesn't it like here? That? So is that faster? It's not the right answer. Not even close. That's U size max. Let me just make sure I don't have the algorithm wrong. Oh, it's R3. But I do the packages, the inputs, the requirement, index, cumulative product, cumulative weight. If I found a weight, I'd return the QE. Otherwise, if I'm outside of the index or I'm over the weight, this isn't a solution. So then I do the left-hand side, which is to say left and right. I mean, I guess technically you are doing a breadth first search of the tree, but you're saying packages requires index plus 1. QE times inputs. QE weight plus that. And the right is the same, but you don't use it. If left is Umax, oh, this is it right here. I return right, left, that. Okay, this way is way faster. So what is this? You basically treat it like a graph. Does this work? Like essentially what you're saying is if try and find the smallest number of ones that equal your weight requirement. You're trying to find solutions that equal your weight requirement, right? So if you ever get it, you return QE. And you keep working down that list. And the way that this left and right works is the left side is what if I add that package to the list, right? Then I want to return that one. The right one is what if I don't add this package to the list, meaning I'm going to skip to the next package. I'll have to think about this one working because it is faster by a lot. So, okay, that's definitely worth investigating. I definitely want to come back to this one. I think we all lucked out on this can partition the rest one. So another combinatorics. Yeah, it's not clear to me why this solution would give you the lowest QE. It's like, presumably if I if I do this, like I reverse them. What am I missing? Why would this still work? Oh, you are still finding them all. So why does this one work faster then? I'll have to think this through, why this solves. Like, my thinking is this one actually does try them all, because the only way to do P1 helper is to know which one it is to have gone through all the other derivative of the P1 helpers. Oh, it's the index, right? Okay. I'll have to think about this. If you know why this solves, I would love to hear it. Okay, this one I think is definitely worth a revisit to figure it out. Like, we're definitely doing a BFS here, but it's not clear to me why the BFS works. So I have to think this through. But anyway, I'll submit it how it is right here, and then we'll do some more refinements and look at it further, just to understand it better. So there you go. With that, I'll say have a great day wherever, whenever you are, and we'll talk to you next time.